Good morning, RPA from Denver, Colorado, the city that um, Governor Christie seems to think that everybody is high and that there's a head shop in every corner, which isn't anywhere near the truth. We are high, but we're 5,280 feet high, and there's not a head shop in every corner. It's every other corner. Just kidding. And the process of joining this organization through this new internet show that we're putting on. Thank you all for attending. This is the Radiant Professionals Alliance, and this is our new program, which we are calling From the Boiler Room. And part of our guests today are Dave Yates, who has currently got his microphone muted because he's also recording this program on his Camtasia to make sure that we have something that we can deliver back to the recording studios and put into our archives for long-term viewing of some of our guests that were unable to attend for one reason or another. And so with that said, I would like to go through some rules of the road. Whenever possible, please use a headphone and with a boom mic if possible. What you don't want to do is to use the microphone that is built into your computer and the speakers that are built into your computer, because it will create a condition of backfeed that will blow everybody's eardrums out. And also ask that you mute your microphones to avoid feedback and background noises, which I was able to actually do from my own screen here. So I have everybody muted with the exception of our guest speakers. When it comes time to ask a question, in the chat box down on the lower right hand side of your screen, you will see a spot where you can actually enter the question and send it to the presenter, which would be me. And what we will do is basically go through the process of interviewing both Mr. Siegenthaler and Mr. Bean, and at the end of each one of their presentations you will be able to ask them a question directly. Once we are completely done with their presentation, then we would go into the open Q&A format, which is where you're allowed to bring forward any questions that you have pertaining to any hydronic heating system, and we will allow everybody to have some input as it pertains to answering those questions. If you would like to ask one of our guests a question, if you would please put a note for Siggy, question for Siggy, and then give me your question, then I will read that to him, and hopefully if everything works out right, it will all be recorded and documented for use in later viewing. So moving on, Dave Yates. Mr. Yates, if you would like to bring your microphone. Dave's asking me to go to full screen. Okay. There we go. Hopefully that's better for you. Now let's see if it will advance for us. Oh, Dan Holohan just showed up. Hello, Dan. Good to see you. Mr. Yates, there you are. If you would like to go ahead and chime in here at this point and tell us who you are and what you do.
He writes for a magazine.
Mr. Yates.
Not word for word.
Mr. Yates. I think I have you muted. One moment, please. Nope, you've got yourself muted. All right, well, Mr. Yates, for some reason, can't hear me, and I will go ahead and tell you who he is. There you are. There he is. Here he is. Okay, go ahead. Uh-huh. There we go. Wow. 70%. That's pretty fantastic. Thank you, Dave. And by the way, this is just a. Pardon? Okay. The I can't do that. I've already let that screen go. I need you to mute yourself. For those who are listening, this is just a snippet of the class that Dave put together for the RPA, and I can tell you from personal experience and having gone in and looked at his class that it is fantastic. And if you want to learn more, definitely hook up with Dave and get into his heat spring class. He's done a fantastic job of putting a lot of anecdotal information into this that you won't find in any book. Dave, I can still hear myself echoing. I think that's got it. It does. By the way, that's a picture of me. That's the new face of Radiant. Kind of glows on you, doesn't it? I think it's actually from being exposed to so much radiation over the years that radiant energy is strong stuff. I'm the executive director of the RPA and have been for over the last year and a half. This job is a whole lot more than I thought it was going to be. Of course, anytime you take on a new job like this, it's a new experience. I've been a member of the organization for the last 20 years, which basically means I've been a member of the organization since it's been around. The RPA is 20 years old this year. I've been a contributing editor to Contractor Magazine. I've been an educator for life. I'm a former expert witness, which basically means I was paid a lot of money to go around and basically find what really nice people were doing wrong in the field. So there's not a whole lot that I have not seen, and there's not a whole lot that I have not done physically myself. And I'd love to bring these experiences to our organization so that we can share in my experiences. And a little known secret is I am a licensed master plumber. I quit advertising that about probably 15 years ago, and I have been a master plumber for 36 years. And in looking at Dave's resume, I see that he's been a master plumber longer than I have, and I didn't realize he was that old. I guess maybe he started working when he was like 16 years old or something. You don't need to comment, Dave. This is a picture of one of the very first radiant wall programs that we put together for the National Renewables Energies Laboratory. And you can notice that there's some nail plates on there. Those were put on courtesy of the local authority having jurisdiction, who did not want any of the volunteers to hit our tubing with nails. And I tried to explain to him that we had a story pole which would keep their screws and nails away from those tubes, but he didn't want to hear it. So we had to put the nail plates up. As soon as he signed off and left, the nail plates came off. And then we insulated the backside of these walls. This is in a Habitat for Humanity house that was co-sponsored by the National Renewables Energies Laboratory. It was also connected to a solar thermal system on the roof, and the system has worked fantastic. I'm a big fan of alternative radiant heating surfaces. I love my radiant floors, but if we as an industry are going to move this industry forward and start providing a greater percentage of the homes that are being built with hydronic radiant heating, we're going to have to look to some alternative methods. And radiant walls, as well as radiant ceilings, are my systems of choice. This is a ceiling in my house up in the mountains while it was under the process of being constructed. It's basically a Roth panel that was designed originally for application on a floor, which I put onto the ceiling, snapped my tubing into it, covered it with a double layer of 5/8 sheetrock because I've got a solar thermal system tied to it, and let her rip, and it works fantastic. One of the common myths, seeing as how this is a myth-busting show, is that radiant ceilings causes your feet to be cold. And I've actually documented my floor surface temperatures at around 74 degrees Fahrenheit when the ceiling was running. So I've killed that myth and have pictures to prove it at some point in time. Quick advertisement. If you are not a member of the Radiant Professionals Alliance, we would absolutely love you to join. This is an organization of the members, by the members, for the members, with the members benefiting from everybody's work. And we've got a whole lot of excellent volunteers, many of which are participating in this show this weekend. And thank you all very much for your participation. This has been one heck of a job, and we've got a long ways to go. We've got code initiatives going. We've got certification programs underway. We have training and education programs underway. And in general, there's a whole lot of stuff going on, and we can use all the help that we can get from all of our volunteers. So by all means, get signed up. It's inexpensive. It's around $300 per year for a contractor. That shouldn't burn too far into your beer money. And I think you'll find that it's very beneficial from the standpoint of raising the bar and getting us all work so that we can move forward delivering the highest degree of comfort known to mankind, as well as getting us into a position of respect from the standpoint of everybody knowing what it is that they're doing and doing it the right way. About the talk show. This talk show was basically a brainchild of my own, which I started working on over a year ago, and decided that we needed to get some of the camaraderie back. That was one of the key points of the original RPA, the old RPA, was the ability of contractors to be able to get together, to talk to like contractors, to find out, what do you do in this situation? If you've got a tie tubing, do you use wire? Do you use ties? What do you do? What's the fastest way to do it? So this is our effort to bring that camaraderie back together. We are having a contest to name this show. By all means, submit it to me. The deadline is November 7th, and we will have a $50 gift certificate to the winner. It will actually be a prepaid Visa that you can spend however you would like. Currently, we're scheduled for every other week guest interviews. And if demand increases enough, Dave and I have agreed that, with the exception of holidays, that we'd be willing to pop in here on a weekly basis to keep people abreast of what's going on. Eventually, we hope to have the ability to be able to play some music in the background so that you also don't have to just listen to our guest or myself rattle on. It will be an open Q&A session following each interview. And we have a large list of people that will be interviewed. And the Q&A session is basically the opportunity for not just contractors, but homeowners or anybody with a hydronic issue to bring it to the floor to allow us to address it. It's virtually impossible to be able to see everybody's problem without having hands-on, but we can at least give you a lot of information that can get you closer to finding a resolution for your problem. These sessions are being recorded, and it will be archived for members only to review at a later date. Another reason for you to join the RPA. This first one will be available to anybody and everybody just so that we can get a sample of the product out in front of our potential contractor members and convince them to join the organization. I want it to be fun, I want it to be educational, I want it to be entertaining, and I want it to be fun. And I'm sure that with all of the folks that we have attending that it will end up being all four of those items. Oh wait, it's only three, but still, it's going to be fun. So if you would like to submit a guest request in order to be an invited guest to this show, you have to be a member of the RPA. And if you have a manufacturing facility or anything, if you're a contractor, if you have something that you think is worthwhile for us to be able to interview with, bring it forward. We're always open for additional suggestions of what we can do to make this show flow. I'm going to move on to hydronic news you can use. ComfortTech 2014 is in Nashville, Tennessee this year. It's September 9th to September 12th. More information available at comforttechshows.com. Dave Yates and myself will be there along with Eric Auney and numerous other well-noted hydronic contractors that Dave and I will be actually presenting classes, and then we'll also be participating in a town hall discussion with a lot of very interesting topics like what are we going to do to find more help. I know everybody I talk to is extremely busy and doesn't have enough help to be able to keep up with it. And we have some solutions. The Scythex show, which is the West Trade Show and Conference, will be November 5th, 6th in Calgary, Canada. I know Robert Bean's going to be there. I know John Siegenthaler's going to be there. I know Dan Holohan's going to be there. And I just found out yesterday that I'll be there too. So if you would like to see some of the work that the Canadians are doing, which I envy them, they're light years ahead of us as it pertains to code initiatives and some of the different things that they've got going, by all means, make an effort to try to show up at this show. And I know that Mike Miller will probably be there too, who has just recently been announced as the chair of the Canadian Hydronics Council. Congratulations, Mike. Couldn't think of anybody else that would be better to be in that position. In January, we have the AHR Expo coming up, which, if you've never been to this before, you're missing a lot. The AHR Expo is basically the North American version of ISH. In my professional opinion, ISH is misspelled. They're missing a W. It should be called WISH, because a lot of the stuff that you see over there will probably never make it to the side of the pond, whereas the AHR Expo is for real. These folks have the product, they have the ability, they have the support. Anybody that's worth their salt is going to be showing at this show, and the Radiant Professionals Alliance has decided to hitch our wagon to this show, and we'll be having our annual meeting and our educational conferences in conjunction with the 2015 AHR show in Chicago. Stay tuned for more information on that. We are formulating a plan as we speak. The quick word on the RPA System Design Showcase Awards program. The information is available at this live link, or if you go to the RPA website, which is radiantprofessionalsalliance.org, there's a pop-down button that you can click on for Showcase Awards information. The application's there, the instructions for filling the application out, recommendations on what you should do if you really want to try to win, and strongly recommend that you join. If you join this, basically, if your project wins, your job is highlighted in a magazine. That is a very handy marketing tool for you to be able to hand out to your customers, and basically get into a situation where you can show them your work that your industry peers have recognized and are willing to share with the rest of the industry. The RPA University Fall course offerings currently are available through heatspring.com. Dave's Fundamentals of Radiant Design is up there. There's another free lecture that Von Woodard put together, which is 4 solar strategies for integrating solar and hydronic heating. And then he's also got a full-blown course that he's putting on there that is basically a course on interconnecting solar thermal into hydronic radiant heating systems. And we have a whole bunch more classes that we're in the process of working, in fact, including myself, putting a program together on an advanced design radiant course. Many of these courses will be a prerequisite for the certification program that is going to be coming to fruition probably in the first quarter of 2015. And I know that Mr. Siegenthaler and Mr. Bean also have some classes there, which I will allow them to speak about. So a little bit about today's guests. Today's guests are John Siegenthaler and Robert Bean, affectionately known as Siggy and the Bean. These two, for those who aren't familiar, and I suspect pretty much anybody that's in this room is familiar with these two, when these two get together, a lot of education happens. And it's a fantastic experience. Anytime I get the opportunity to go listen to these two guys, I take it, because I always come away with something new, something I hadn't thought about. They're both fantastic educators. And real quickly, John, if you'd like to jump in here, I'll let you start talking about yourself. This is John Siggy Siegenthaler. This is his most wanted poster picture that I took off of the wall of the post office. John?
Okay. How's the sound, Mark?
Great. Sounds good.
Okay. Well, thanks for the invitation to get on the program today, and thank everybody who's joined in. I've been involved in hydronics for a little over 30 years now. We've done design of systems using all different types of heat sources, primarily in residential, light commercial projects. Of late, doing a lot of writing, getting involved with more online courses, and working on another textbook. So plenty to keep me busy here. The classes on HeatSpring, I'll just mention quickly. This is the same organization that's hosting the classes that Dave does for the RPA. We have a course called Mastering Hydronic System Design. It's a 10-week online course. Pretty detailed, very design-focused. That'll be, well, it's run twice, and we'll be starting that up again on September 15th. And then a brand new course called Hydronic-Based Biomass Heating Systems, where we're focusing on wood-fired heat sources. I should say high-efficiency wood-fired heat sources. Wood gasification boilers, pellet boilers, and chip boilers. And what are some of the hydronic details, some of the components and subassemblies that we can use to really leverage the efficiency of these boilers? Seeing a lot of interest in biomass boilers, especially in the northeastern U.S. And this course is really, again, a design-focused course. Again, it starts up September 15th. If you go to the HeatSpring site, you can take a look at the outline and take a look at some sample lectures from that. So, Mark, go to the next slide. Okay.
As noted here, please hold your questions for John until the end, unless it's really, really important and it's something relevant to what it is that he's saying, and then we'll flow through this much smoother.
Okay, so Mark asked me to put together some myths. There's a lot of myths in hydronics. I'm sure there's a lot of myths in any technology, but these are 4 that I wanted to talk briefly about here today. And I just run down through here. The first myth, that residential hydronics is only good for heating. It's true that most people know hydronics in the context of heating, but we can also use it for cooling, and that's definitely a sector of the industry that is rising now. Myth number 2, pumping away. It says here, pumping away refers to the boiler. I think there's a fair amount of people that assume that's the case, but I think Dave mentioned earlier today, it's really pumping away from the expansion tank, and we'll show you some examples of that. The third myth, plateless staple-up tubing is acceptable. I can tell you from looking at projects in North America and looking at techniques that have been used in Europe over the last 20 years, I have never seen a plateless staple-up system in Europe or anybody advocating it. So it's a potential problem. I probably shouldn't even use the word potential there. It's a likely problem, and we'll show you why. And the last myth, and this is one that is particularly appropriate as buildings become more energy efficient, is that if a radiant floor doesn't feel warm, it's not working. So we'll try to dispel that. Okay, Mark, let's go to the next slide. Okay. The fact of the matter is that water is a superior material at moving heat compared to air. If you look at the physical properties of water versus those of air, water's about almost 3,500 times better at absorbing heat compared to air on a volume basis. So a cubic foot of water for a 1 degree temperature rise can hold almost 3,500 times more heat than that same cubic foot filled with air. And of course, this is the science behind why we can use small tubes, 1/2 inch, 3/4, 1 inch, compared to fairly large ducts, maybe a 10 inch by 20 inch duct, if I remember, is roughly equivalent to about a 1 inch pipe carrying water. Now, again, I want to encourage you, if you're involved, especially with heat pump technology today, it could be geothermal heat pump systems, or it could be air-to-water heat pump systems. If you're involved in either one of those, you have a machine that is capable of producing warm water, of course, for low-temperature radiant panel heating during the heating season, but you also have a machine capable of producing chilled water. And the same properties that make water ideal for heating really do apply to cooling, because really cooling is just a matter of moving heat out of a building rather than moving heat into a building. So down at the bottom here, I threw in a quick schematic that shows an air-to-water heat pump, and there are several of those on the North American market now, and certainly I hope more to come in the future. And essentially, in the summer, this is acting as your chiller. It's producing, in this case, a chilled glycol. The glycol is in that outer circuit between the heat pump and that heat exchanger. You see the heat exchanger to the left of the tank. It's there to protect the heat pump in the winter, assuming it's in a cold climate. The chilled glycol transfers cooling effect, or better stated, it absorbs heat from the secondary side of the heat exchanger, which is passing water into that buffer tank. And then over on the right side of the buffer tank, I'm showing 4 small air handlers. And one of the nice things about a chilled water cooling system is, especially in larger buildings, think large, sprawled out residential projects or light commercial projects, it's possible to locate these small air handlers in different areas of the building, and you might only be running 5/8 or 3/4 inch flexible tubing from the mechanical room or wherever this thermal storage tank is located out to these chillers, instead of running a trunk duct around through that building. You can very easily zone the system, same type of techniques that we've talked about with heating, and it's also good application for some of the new variable speed pumps that are on the market now. Okay, so again, I'd encourage you to take a look at some of the chillers that are out there. There's even gas-fired chillers that are at a capacity level appropriate for residential light commercial systems, and all these are potential sources of chilled water. Okay, let's go to the next slide. Okay, pumping away refers to the boiler. The fact is, no, when we talk about pumping away, we're referring to the expansion tank location, where the expansion tank ties into the circuit. Over on the left, you see an incorrect piping setup. I label it incorrect, but there's probably hundreds of systems out there in the U.S. and I'm sure some up in Canada that are piped like this. Sometimes it was a matter of convenience. Boilers used to be shipped with the circulator actually installed on the boiler, and it was typically installed on a return side to keep the packaging size down. But if you look at that and consider that boiler is really just a wide spot in the piping, there's very little pressure drop or head loss across a typical cast iron sectional boiler. So effectively, most of the pressure differential that circulator creates is being dissipated out there where you see the baseboard. Okay? And very little of it is actually being dissipated between the discharge side of the circulator and where the expansion tank taps into that system. So what's going to happen when this circulator turns on is that the static pressures that are present out in the piping system between that expansion tank and the inlet side of that circulator, the static pressures are going to go down. And if there are air vents located out there, or even valves that might have slight weepage on the packing, there's the likelihood that air could get back into the system. Now, that'll happen if the pressure in the pipe goes subatmospheric. If there's a low static pressure, or if the system's fairly tall, you could have very low or even zero static pressure at the top of the loop. With an air vent there, when that circulator turns on, you could actually suck air right back into the system. Over on the right are a couple ways to fix that. The upper schematic just moves the circulator, so again you can see it's pumping away from the location where the expansion tank taps into the system. And then the one in the lower right is also acceptable. Again, when you have a heat source with low flow resistance. Effectively, from a pressure drop standpoint, you can almost forget about the boiler even being there in the circuit. The pressure drop is so low. So even though the expansion tank is on the inlet side of the boiler and the circulator's on the discharge side of the boiler, the pressure drop between that expansion tank T and the inlet of the circulator is very small percentage of the overall pressure drop. One advantage to keeping that expansion tank in that location is there's less heating of the shell of the tank, especially if the tank is piped fairly close to the pipe. The water temperatures are a little bit lower on that side of the system. So either of those schematics would be an acceptable way to set up that system. Okay, let's go to the next slide.
John, quickly before we leave this, I'd like to tell people as an educator that this is probably one of the hardest concepts to try to get through to contractors in the field. It's hard to see and to envision in their own mind. And at one point in time, when I was working as an expert witness, we had a lawyer who was questioning on this and saying, this is BS, we don't believe this. And we put together a 4 by 8 foot panel that had a 3/4 inch loop that basically ran around the exterior of the panel, with the expansion tank hanging in the middle with an air separator, and then a circulator moving towards the expansion tank and a circulator moving away from the expansion tank, with pressure gauges, large 6-inch diameter pressure gauges on each corner of this board. And when we turn on the pump that was pumping away from the point of no pressure change, you could see the pressure increase and then slowly decrease until it came back around to the expansion tank again, where it was basically at the static fill pressure. And when we turn that pump off and turn the pump on that was pumping towards it, all the gauges to the left-hand side would all go negative until it came back around to the gauge that was right at the outlet of the air separator, where it would be back to static again. And it was so graphic that they dropped that charge immediately. And it disappeared.
So you have a lawyer that now understands pumping away.
I do. He's got a video of it.
Okay, good. Okay, myth number 3, plateless staple up is acceptable. We've received a lot of calls over the years, emails and so forth, and the complaint is typically that the floors are not properly heating the space. Maybe the space is at 62 degrees where the thermostat is set at 72 degrees. One of the first questions I ask is, how is the tubing installed? Is it stapled to the floor framing, like you see in that upper left corner there? That's actually stapled. That's a 1/2-inch PEX tube, which is clipped to the lower cord of the floor truss. And in the lower left, looks a little neater, but again, that tubing is clipped into the joint between the upper cord of that wooden I-beam and the web of that beam. And you don't see any heat transfer plates in either one of these. This is a really bad idea. I refer to this as a thermally constipated system. And the reason I say that is we could put water even at 160 or 170 degrees Fahrenheit through that tubing, but we have very, very poor what I call heat transfer geometry. That's a kind of a combination of materials and shapes and surface contacts to get the heat from that tube out to the top side of that floor, especially if you look at that photo in the upper left. How are the BTUs supposed to know where to go? So under a very light partial load condition, you might trickle enough heat into that cavity to maintain comfort in the space. But when it's 10 degrees outside or below 0 outside, there is no way either one of these is going to produce enough output. And just to show you kind of some of the engineering behind it, over on the right is a graphic that I did several years ago. And actually, this was actually a graphic that was done for some of the original RPA training materials. And what I did is I used a piece of software called finite element analysis. And we modeled 1/2-inch PEX tubing, 8 inches on center, under a subfloor. And you can actually see the subfloor lines there. It's a 3/4 inch plywood subfloor, and it looks like 3/8 hardwood on top of that. And on one model, we included aluminum heat transfer plates. These were 6-inch wide plates. These were actually the thin plates, 24 thousandths of an inch thick plates. And we put the properties of the aluminum in, the properties of the fiberglass and the wood and so forth. And what a finite element program does is actually models a 2-dimensional heat transfer. And you can see here that the plates are doing a good job at diffusing the heat away from the tube. That's their function. They're not there to reflect energy. I've heard people use that term because the plates are shiny. Right. They're there to conduct heat, like just like a wick moves wax in a candle. These plates essentially wick heat away from the tube and diffuse it out across the underside of the floor surface. And you get a much higher output. You have a higher average floor surface temperature for a given water temperature, and in round numbers, almost 3 times the heat output for a given water temperature. That's really important because we're working with low water temperatures, relatively low differentials between the water temperature in the tubing and the room temperature, and we really want to maximize our radiant panel, be it a floor, a wall, or a ceiling, we want to maximize its performance as a heat exchanger. It's really what it is. It's a water to room side heat exchanger. Now, the lower graphic is the same as the upper graphic with the exception of the plates being removed. And you can see those colors are very much crowded in around the tubes, and that's indicating very poor lateral heat diffusion away from the tubes. And again, if you look at the graph up above, it's a little small, but a couple things I'll mention. One is the output is roughly about a third of the BTUs per hour per square foot that you'd have with the plates. Secondly, you can see that there's more peaks and valleys involved. That lower red curve, it tends to look like a couple mountains side by side. And that's a phenomenon called striping. And what that means is we're going to get a hot area on the floor right above the tube, but the temperature is going to fall off very quickly as we move away from the tube along the surface of the floor. And if you can take your hand and move it across a heated floor panel, or for that matter, any radiant panel, and you can feel where the tube is very distinctly, and then a relatively quick change as you move your hand away from the tube, that's generally not good. The ideal radiant panel, the ideal one, would have a uniform surface temperature. We can approximate that with tubing at various spacings, and of course the closer the tube is spaced, the better the approximation. But the presence of the aluminum plates makes a big difference. So if you're designing radiant panels, be they floor, wall, or ceiling panels, and you're intending to use that with any type of modern low temperature heat source, it could be a ModCon boiler, it could be solar thermal, geothermal heat pumps, even a wood-fired boiler, because we're trying to draw the thermal storage tank associated with that wood-fired boiler down to low temperatures before we refire the boiler. Low temperatures are extremely important in modern hydronic systems, and the plates really enable that type of performance. Okay, let's go to myth number 4.
Before we leave this, I'd like to reiterate that basically what you're saying is conductivity is the king of heat transfer. That radiant off the tube and convection within that joist bay are there, but the conductivity is what's really going to make the difference as it pertains to the surface temperatures on the top of that floor. And by the way, that picture in the upper left-hand corner there where they actually have the tubing fastened to the lower cord of that scissors truss, it's getting its marching instructions on where it's supposed to go from the aluminum foil that's underneath it, John.
Yeah, it's going to help. It's going to help, but
Robert,
that photo was actually taken by a contractor in the process of tearing this out and getting ready to do it right. So
I'm sure Robert Bean could probably do one whole session on nothing but aluminum foil type of radiant barriers.
Yeah. Actually, Robert, I think, is going to address this too. We were talking, I think it was just a couple days ago, about the use of radiant panels in low energy use buildings. As building codes tighten up insulation requirements, we're seeing design heat loads that might be on the order of 10 BTUs per hour per square foot of floor area. And just to show you an example here, I took a 2,000 square foot well-insulated home and assumed it had an 18,000 BTU per hour design heat load, and further assumed that 90% of the floor area was heated. We don't put tubing in stair openings or under kitchen cabinets or under refrigerators. So we have 1,800 square feet of floor area to deliver 18,000 BTUs per hour under design load conditions. And you can see the math there. It just, if you take the design load divided by the heated floor area, at design load we only need 10 BTUs per hour to leave each square foot of floor. The next formula down is just, it's an approximation of average floor surface temperature. Okay, the floor surface temperature does vary from over the tube to between the tubes and so forth, but if you would assume an average floor temperature to deliver 10 BTUs per square foot per hour into a room that's at 68 degrees Fahrenheit, the average floor surface temperature only has to be 73 degrees. And what I'd like to do is just have people put their two palms together and hold it for a minute and ask what temperature are they feeling. And oftentimes somebody will kind of quickly say 98.6. And I point out, no, you really have to put your palm somewhere else to feel 98.6. But if you put your palms together, you're probably feeling a temperature between 82 and maybe 84, 85 degrees. So if you put your palm on a floor that was at 73 degrees, how is it going to feel? And again, somebody will say cold. And that's not really true. And Mark, you were pointing this out, even with a radiant ceiling. A low temperature heated floor, or even a floor receiving radiation from a radiant ceiling up above, is going to be warmer than that same floor in a building with any type of convective or forced air heat. So what the math is telling us here is that a floor that averages 73 degrees is all that's necessary to maintain that building at a 68 degree interior temperature under design load conditions. Now imagine a half load situation. Maybe it's, instead of 0 outside, maybe it's 35 degrees outside. Under half load condition, we'd be down to probably around 71, 71.5 degrees. So it's not a matter of the floor properly heating the space. It's a matter of what your customers' expectations are. If they've been in a building with a higher energy requirement, maybe 3 times this, maybe 30 BTUs per hour per square foot, maybe they've put their hand or their bare foot on a floor that was at, let's say, 85 or perhaps even a little warmer than 85 degrees. And they detect that there is heat flow from the floor up into their hand. If they put their hand on a floor at 73, they aren't going to detect that, and yet the space is still being heated. So it's important not to overpromise what I call the barefoot friendly floor. The photo that you see there is actually one I took in my office. I have a slab type floor heating system in the office. You can see where the return bends on the 2-bar, and an opportunity to borrow this $30,000 camera, infrared camera. So I wanted to shoot as many images as I could in the week that I had the camera. So one day I just took off my shoe and sock and stood there on the floor in the office for about a minute, and then just stood back and took a photo where I was standing with the infrared camera. And you can see that my foot was warmer than the floor. Heat would be conducting from the bottom of my foot into the floor, but I can attest to you the floor wasn't cold. It was not uncomfortable. Okay? So just be aware of the fact that if you are dealing with very low energy use houses, and you know, there's various degrees of that out there. About the lowest energy use house that I've heard of in the U.S. at this point is called passive house, and I think even at 10 BTU per hour per square foot would probably be a little bit high for a passive house. Mm-hmm. But even houses that are meeting Energy Star requirements, for example, they can definitely be heated with radiant panels, be they floor, wall, or ceiling, but don't promise that somebody is going to have a toasty warm floor even under design load conditions. The floor simply doesn't have to warm up to the condition that it would in a much more energy wasteful house. So
all good points. You know, I actually had a student that had taught a course up at Colorado State University that became a building contractor of passive houses, and he called me up a couple of years ago and said, hey, I've got my first passive house. I've done all of our own energy load calculations, and I need some assistance from you in configuring a system for it. And I said, well, what are your loads? And he said, 5 BTUs per square foot. And I said, per hour? And he said, no, per year. I'm like, 5 BTUs per square foot per year? I said, you could heat it with human bodies. And he said, I know. He said, the problem is I can't keep the human bodies there when it's at design conditions, so I need some means of being able to deliver heat to this space. And they ended up using a heat recovery ventilation system with some toaster elements in the ductwork because they had PV on the roof and stuff, and they got it figured out. But their basic major loss was the windows. And at that point in time, I was heavily into the radiant windows, and I said, you know, you could use the windows to heat the house if you wanted to. And unfortunately, it wasn't in the budget, and it didn't work out. But, you know, when we're talking about loads of 5 BTUs per square foot per year, mm-hmm. You don't want to tell them that they're going to have warm floors. And we as an industry are guilty of selling the concept of warm floors and not focusing on the fact that we can deliver radiant comfort regardless of whether the heat emitting surface is a floor, wall, or ceiling. And I love all of my different methods, but quite honestly, I think that radiant ceilings are the most misoverlooked opportunity that there is from the standpoint of new construction and retrofit, and being able to deliver that radiant comfort factor that people don't care where it's coming from. As long as they're comfortable, that's the important thing.
Yeah, good points.
We have some questions for you, John. Do you have anything else to add?
No, I'm open for questions.
Okay, the first question came in from Dan Bastian. It said, question for Siggy at some point, plateless staple up is not acceptable. Does this include installations with EPDM tubing?
I would say yes. There may be differences of opinion out there. Really, the tubing material itself, be it PEX or rubber tubing, PEX aluminum PEX, really makes very little difference in terms of heat transfer. It's the surrounding materials and how they connect to that tubing that is the dominant determination of heat transfer.
You know, to his point, and I understand where he's coming from, I think they've done a significant amount of work with Watts, and Watts is the only supplier of any kind of a EPDM-based rubber tubing. In their installation manual, they like to see the staples as close to each other as they possibly can, so they get what they call the squish effect. If you think about a circle being in contact with a flat plane, the amount of physical contact that you have at that point is minuscule. And if you're using rubber tubing and you're stapling at 6 inches on center, you get more of a elongated squish effect with that tubing actually getting more surface contact with it. And it probably is better than just a bare naked PEX tubing that's in contact with the flat surface. But I still agree with you that any way that you can enhance conductivity is going to lower the temperature of operation, which is going to equate to a better energy savings, a better comfort condition throughout the whole system. My personal opinion has to stay off because this is being recorded, but I have never done staple up. I did staple up one time. The customer called me back the next year and made us rip it out and put it into heat transfer plates because every time the system started up, it sounded like a herd of crickets running through the floor, which is just basically the nature of PEX tubing as it goes through its expansion and contraction.
Yeah, and you can minimize that. You can minimize it with constant circulation outdoor reset control, so you have very gradual changes in temperature occurring in your tubing.
You can, but you know, if they'd have put it in plates, we wouldn't have been having that conversation in the first place, and we'd actually forewarned her. But she said, no, my brother-in-law said, this is the way to do it, so I want you to do it this way. And I said, okay, sign here, stating that we notified you that it would be noisy.
Yeah.
And, ended up going back in and tearing down the ceiling in her basement and putting in the plates, and it was great. I mean, the system performed as expected. The supply water temperature was reduced significantly over what it was before, and all in all, I think it's just a right way of doing it. Rich McGrath has a question for you. He says, what are John's thoughts on thermal storage below or above ground, replacing ground loops as source for heating and cooling, connected to heat pumps and receiving energy from multiple sources?
I'm assuming he's talking about some type of maybe a large concrete tank in the ground.
I believe
that
so.
would
Sounds
be
like what the Euros are doing.
Yeah, honestly, I don't know. Without running numbers on something like that, it would depend on how much of the Earth is actually being engaged thermally. You know, the tubing versus the tank, and without having specific numbers on the size of the tank and the depth of burial and so forth, it's hard to say. It's a possibility. I'm sure probably some people have experimented with it. I haven't, so all I could say is, you know, we'd have to run the numbers and just see how does it compare to burying some tubing.
I know that the Europeans, and actually Colin Wonder is listening in on this, and if he's good, I might unmute his mic later. Colin is actually the chairman of our public policy committee who keeps an eye on what's going on in Washington, D.C., and Colin has personal experience with these underground ice storage systems, and I know that John and I have had this conversation before about the fact that if you've got it insulated and it's in the ground and you're taking it to 32 degrees Fahrenheit, the differential between the outside surrounding soil and the inside water is less, so your tank standby is less. And the Europeans are really heavily into this. You know, I have a friend of mine that is from Germany, the Heatmeister, and every time he goes over there, he comes back with great ideas, and he's telling me it's in ice. He said our future is in ice, and also Pietra has a lot of experience with that. And I think we're going to see some changes in the way that we do business as it pertains to heat sources. You know, the boiler 20 years from now will probably be in a museum, and people go, "Wow, what is that? What did that used to do?" Follow-up note or a comment actually from Dan Bastian said, "Yeah, the squish effect is what I've heard, but he's always been skeptical. And squishing may increase your surface area by what, 30%, and 30% of a little tiny area."
You know, just to address that, I think it was Bob Rohr several years ago that took a piece of tubing and I believe it's rubber tubing and put some yellow paint on it and then stapled it up to the floor based on somebody's specifications for staple spacing. Mm-hmm. And then basically pulled the staples out, pulled the tubing away, and looked at the paint that was left on the underside of the subfloor from doing that. And it was... I'll just say it wasn't quite as much paint on there as what the squish tube factor might imply it would be. So for what it's worth, I'd save the money on the staples and invest in the plates.
Yeah, I think that, what's your opinion as it pertains to the light aluminum flashing versus the extruded aluminum flashing type, or extruded aluminum type of heat transmission?
Well, you know, we did some finite element analysis work on that, and I should, you know, disclaimer up front, anytime you're working with finite element analysis, you make some assumptions like the contact between the outer surface of the tube and the plate itself, and we assume we had good contact there in both cases. What we did is we modeled a thin plate, and we looked at the cross-sectional area of the thin plate, and then we created an extruded plate that was twice the thickness on the fin, but using the same amount of aluminum. So it would be approximately half the width. And it was an interesting comparison, and we actually found that the thin plate would outperform the extruded plate under that condition. So if you had a given amount of aluminum and you had a choice of manufacturing that into a thin plate, let's say maybe 8 inches wide versus a thicker plate at 4 inches wide, what's called the fin efficiency of even a thin aluminum plate is actually really good, pretty close to its theoretical maximum. So you don't gain a lot in the thickness of the plate. Now, again, there are people with differences of opinion on that, and some of it is based on the contact between the outer surface of the tube and the socket, if you will, the trough in the plate that the tube goes into. If the plate's bent up, or if it's one of these homemade plates that I've seen where people take some roof flashing and just kind of bend it up around the tube, it's not going to perform very well. That joint between the tube and the plate is very important. But if we made an assumption that on both a thick extruded plate as well as the thin plates, if we had the assumption of 180 degrees of wrap, if you will, okay, from basically around the bottom side of the tube, as long as we had equal contact in both cases, the finite element analysis showed some performance edge, not a huge one, but maybe, if I remember right, maybe a 20% performance advantage in going with the thinner and wider plates.
It's good to know. Those are the things that we would, as an organization, would love to be able to actually physically test. And I know I did a lot of research and development when I was still working with the Red Rocks Community College, and still have some of those reports someplace in my archives files. But these are the kind of things that everybody wants answers to. And
yeah, you know, we're talking plates here too, Mark. Just point out there are graphite plates on the market now too. Mm-hmm. And what we've seen of those, that they're performing quite well relative to the aluminum plates, equal or in some cases slightly better than the aluminum plates.
Now, if we can figure out a way to convert all that carbon dioxide in the air into carbon for heat transfer plates, we'll have it made. All right. John,
okay.
Thank you very much. I don't have
You're
any
welcome.
other questions. And our next, we've got the questions answered for John. Mr. Bean.
Hello.
Good morning, sir. Welcome.
Good morning.
It's great to see your smiling serious face there in the photograph.
Yeah, well, that's when I was much younger. Today I'm grayer and much more grumpier looking.
I wouldn't say that. Well, here's your profile. In case you forgot, go ahead and give us a little bit of history on yourself and what you're.
Well, up to a lot. We've had just a really busy year around the continent. One of the key things that we were working on this year was actually there's a collaborative effort between HRAI, CIPH, TICA, and COA, which are the four major organizations in Canada. And that collaboration was really to establish a memorandum of understanding about education and the quality of installations of and designs and inspections of HVAC systems in Canada. So that was a huge step forward for the four major organizations to get together and write a positions document on that. And so we're still meeting every once in a while to talk about how we can improve design, installations, and inspections of systems in Canada. The other thing that we've been really busy at, and I'm going to blame Devin Avalon from Uponor for this because he's our ASHRAE TC 6.5 program chair, and Devin has been incredibly skilled at arranging education programs for our TC 6.1, which is our hydronic, 6.4, or 6.5, which is our radiant, and 7.4 exergy. So we've been doing a lot of courses for all of the conferences on hydronics and radiant and snow ice melting systems, and as well heavily involved in the SSPC 55, which is the thermal comfort standard for those that aren't familiar with it, and we've been very busy in that. And 55, of course, is very important for those that are involved in radiant heating and cooling, because the 55, which is about thermal comfort, has a big component of radiant in it. And so if there was ever a standard within ASHRAE that the radiant industry should get behind, it would definitely be the standard 55. We just finished up a seminar for CIPH for the inspectors in Canada on CSA B214, and that was very well attended. In fact, it looks like we're going to do a second one. There's a big demand for it, and with Mike Miller on the line, of course, he's very familiar with the CSA 214, and I understand they have a meeting coming up to look at their future revisions on that. You've already mentioned the SciFex West, so I'm looking forward to that. Going to be able to have a chance to speak with Dan Houlihan and John Siegenthaler on that. I guess we have a round table, so that's going to be a pretty exciting event. And then two last things, of course, we've got a big program coming up with HeatSpring and B&P Media, and it's on integrated design. And what we're going to be doing in that 10-week course is, you know what, it's just really a place for me to dump the last 34 years of knowledge into a course so I don't forget it. And, so we're going to be taking everything that I've learned about indoor environmental quality, about building science, about mechanical systems, energy efficiency, exergy efficiency, and we've put it into a 10-week course. And it really is it's not for the newbie. There's an expectation that students of this course have an engineering degree or a diploma at a technical college, or they have a certification, high-level certification from organizations like RPA or the other organizations in Canada. And so if there's anybody online or you know anybody in the industry that has sort of gone to their level of understanding but want to take it a next step up, that's really what we're catering to. And then other than that, gents, we're just still dumping stuff into healthyheating.com. We have, I think, over 900 pages now, addressing everything from, again, the building and the health sciences to energy to systems, and it's all there. So that's it, Mark. That's what I've been up to.
You're a very busy person, and thank you very much for all of your contributions to our industry. Are they going to be is ASHRAE going to be writing a new book once they purge your brain? You call it the Book of Beans.
No. Well, I'm just a small cog in the wheel. There's a lot of really great people within the ASHRAE organization that are a lot smarter than I am, and I
haven't met them.
We contribute to the handbook. Now they're there, they're there, and we contribute to the handbooks, and that's sort of where and of course all the educational programs that we have. So they're in writing somewhere. They're on record.
Well, quickly, as you can see from the slide,
so
I
that's
wanted you to tell us what the heck is a CHIAOE, or what we call a CHOWE.
I can't remember if that was you or Dave that came up with that acronym, but that's the Carlson Houlihan Industry Award of Excellence. And you know what? It's been a lot of fun, and we can thank Dan Houlihan for really providing the DNA, which is, of course, Gil Carlson's wheel that John's holding there. And that was the original one. And so we've turned it into an Industry Award of Excellence, and it gets awarded every 2 years. And I know John Barba's online, so he's also one of the recipients, and everybody else, of course, is online. So it's been a lot of fun.
Yeah, we actually have what I guess you could call it 5/6 of the Chowies present in this particular meeting room, which is fantastic. Thank you all for attending. And we're just missing Ken from Canada. And in case you happen to be under a rock or in a cave, basically, John Siegenthaler is the most recent recipient of that, and congratulations to him. He's going to do an excellent job of carrying it forward and letting people know how valuable that tool is. And it's hard to conceive, but that device that John is holding there is basically the base root of all of the hydronic formulas that are used throughout the industry. And to have the opportunity to actually hold that in your hands and look at it is really fantastic. And again, I'm honored to be a part of it. I was going through your website trying to find this picture, and came across a picture of me when they gave it to me, and I was a blubbering idiot. I couldn't believe it. I just lost it. It's like, I'm not deserving. I'm not deserving. And oddly enough, it was at that point in time in my life when I thought I was going to quit being a wethead and become a watthead with the radiant windows. And Dave Yates and I were sitting in the bar the night before, and he said, so you're going to be here tomorrow showing stuff? And I said, yeah. I said, Dave, I'm going to have to make an announcement. I said, I'm leaving the industry. And he looked at me and he said, you can't do that. And I didn't know it at that point in time, but he was aware, as well as you and everybody else, that I was going to be receiving the Chowie Award. And he never even broke sweat, didn't say anything. He just said, you can't do that. And I said, well, I said, I'm not leaving the industry, but I'm no longer going to be a wethead. I'm going to be a wathead. And the next day, I'm standing there showing the radiant window and stuff, and look, and all of a sudden Robert Bean walks past me, and it's like, what the hell's Bean doing here? And then they spray.
Yeah, I was coming back from a conference. I can't remember where I was. I was somewhere in the south, and I knew you guys had something going on. And well, it was Dan. It was one of the round table discussions that Dan was having. I think it was.
Yeah.
And
it was
so I
wet stuck.
That's right. It was a wet stock, so I diverted my trip home and dropped in and dropped that on you.
Well, thank you. I'm still in shock. I have yet to recover, and
yeah,
I'm sure Barbara and everybody else that has received it since then is probably in the same boat.
Yeah. Hey, so while we're talking here, I was just going back to some of the comments that John was making, which were really, really good. John, one of the things that we should think about it in terms of these finite element analysis, because we both do it, but that is looking at plates, and rather than doing it in two-dimensional, do it in three-dimensional and see what the effect would be between a thin plate and a thicker plate. Yeah. I think we might find some differences when you model it in 3 dimensions, which means looking at not only sort of a set strip, but looking at the linear effect. What happens when you fasten a pipe in a thick plate versus a thin plate? What happens as you travel down the pipe? Does it make a difference as opposed to just sideways? So I think that would be neat. And then going back to that comment about your foot on the floor, people need, oftentimes they forget we actually need to get rid of heat or we die.
Yeah.
And so retaining heat is not a good thing. It's like retaining water. You don't want to do that either, right? So these discussions on floor temperatures are important because people can feel comfortable at low temperatures on the floor, and the feet are a very good way to shed heat. So in a high performance building, of course, the body has less ability to get rid of its heat, and so it's important to get rid of heat, otherwise you overheat, and which of course is not good. So the floor is actually a good place to do that while you're still being comfortable. So anyways, just a couple of comments on John's stuff. So
You know, I had a hydronic near-death experience once that I don't ever care to have happen again. Literally saw my life in a boiler flash before my very eyes. Are you ready, Robert?
I am.
There you are.
Right. So I'm gonna in my slides, I'm just gonna take on one myth, and that has to do with radiant cooling and condensation. And the number one statement, and you can all write this down and you can use it, and that is that 100% of all condensation and mold problems in buildings conditioned exclusively with air did not have radiant cooling panels to blame.
Good point.
Did you get that? So all problems, and the thing is that there's hundreds of thousands of buildings out there that have condensation and mold problems that are conditioned exclusively with air. They didn't have the moisture and the condensation problem because they had radiant cooling panels. So it's not the HVAC system's issue; it's a moisture issue. And so when you deal with the moisture, you then enable the use of radiant cooling systems or anything else that you want, for that matter, in the space. So the next 6 slides are really just snippets of information that industry can use to combat this myth that you can't do radiant cooling. And the first one has to do with preservation of materials. And so one of the best places to get information on indoor environmental quality is actually the museums, because the museums have to maintain very strict indoor environmental conditions to preserve materials. And one of the things that they're concerned about, of course, has to do with high moisture content, because that can then lead to mold in very old books. So this is just a table that I created out of using one of their calculators, because they have a couple of online calculators that say, you know, when you put this temperature in at this relative humidity, this is really bad for books and woodwork and that kind of stuff. And you can see that when you get down into the 35% relative humidity at the temperature of 73 degrees, that there's no risk. And so, in fact, when you get down into the lower humidities, there's no risk to the artifacts that are in the museum. So reason number one that you can do radiant cooling is that the fact that you need to control moisture so you don't wreck stuff. And so that's the number one. Go ahead, Mark, flip the screen, we'll go to number 2. The second thing has to do with microbials. So we're talking about bugs and bacteria and all other kinds of stuff that are nasty in the environment. And this particular graph, which has been used a lot in the industry, it was recently updated in the ASHRAE handbooks, basically tells us that if you can maintain relative humidities between 30 and 60%, you're going to keep the bad stuff at bay. You're not going to stop it completely, but that's the safe zone. So to keep the nasty stuff out of our indoor environments, we need to control the humidity. And if we control the humidity for the bugs and for preserving materials, then we can use radiant cooling without the concerns of condensation. Next slide, Mark. Okay, the next one has to do with control of vapor pressure. So like anything else in science, high temperature wants to go to low temperature, high pressures want to go to low pressures, and high vapor pressures or high moisture content wants to go to low moisture content. So if you want to create a problem in a space, put in lots of moisture and raise its temperature. And by doing that, it's like blowing into a balloon. The moisture from your lungs ends up in the balloon and it expands it, and it's creating pressure on the sphere. And so that wants to relieve itself, so it goes from high to low pressure. And because the balloon has no strength capability, it's got elasticity, it expands. Well, it's the same. If you put moisture in a space and you heat it up, that vapor pressure that's created is going to want to go places. So it's going to go into the wood and into the drywall and into the floor coverings. And if there's enough vapor in the space, of course, then you can then start to support the growth of molds, and you can make it really nice for things like dust mites to exist. And of course, you can start to cause wood rot and all these other things. So another reason that we need to control moisture in a space, independent of the HVAC system, is just to protect things, to make sure that we're not moving high quantities of moisture into low moisture areas that can have a problem. So go to the next one there, Mark. So the fourth reason that we want to control moisture is that the bad things that we put in buildings that contain VOCs, volatile organic chemicals or compounds, that emission rate from those materials, paints, for example, or whatever, the emission rate is a function of the humidity. So if you want to maintain the integrity of building materials, then don't expose them to high levels of moisture. It's not that complicated. And so this is another reason why we want to control moisture, is to make sure that we reduce the amount of emissions from building materials. So let's have the next slide.
Well, before we leave this one, I just have to make a note. This looks extremely a lot like a hockey stick. Just kidding.
Let's not go there. Let's not go there. All right, and then one of the final. I think we have one more, but this one here talks about the dimensional stability of hygroscopic materials such as woods. And so we know that when you have high moisture content in a space, materials like wood, that if they're dry, they become an absorbent. They take in the moisture, and by taking in the moisture, they expand their dimensions. And so that's what causes wood to buckle. And of course, then as it gives up its moisture, if there's a change in moisture, then it dries. So it expands and contracts, or swells and shrinks is probably the better term, as a function of moisture. So if you want to have materials go through these dimensional changes, then allow high quantities of moisture to exist in the space and bring in dry materials. Of course, we don't want that. And so what we know is that dimensional stability of wood actually exists in the values that you can see there down at the bottom of your screen. So between 70 and 80 degrees Fahrenheit, in between 40 and 60% relative humidity, plus or minus 10%. So that's really where we want to control the moisture content. So let's have the next slide, Mark. I think it's the last one. Oh, we got I guess two more. And this has to do with respiratory comfort. So the smart people in Denmark, and there's a lot of smart people in Denmark, that have done research work on indoor environmental quality and the effects of temperature and humidity in the space. And what they found, as many researchers have found, is that when you can control the humidity, again, in that sort of 30 to 60% range, in the sort of typical ambient temperatures that you would get for heating and cooling, 68 to 75, 76 degrees Fahrenheit on the Fahrenheit scale, or inch-pound scale, that you're going to have the least amount of people dissatisfied with the space. So again, another reason why we need to control humidity. So I think this is the last slide, the next one. So let's
that PD that's showing there on the lower right-hand side with the curves that are going across the chart diagonally are percentage of dissatisfied?
Yeah, that's the mad factor. How many people are going to be mad?
What, 70%
or
of people
dissatisfied?
have forced air heating systems? They're probably mad. There you are.
They're probably mad. All right, and then I think everybody here on the screen is familiar with this. This comes out of the ASHRAE Standard 55. It's the graphical tool for defining the conditions necessary for comfort, or to have the most people happy or the least people mad. And again, if you follow the lines of humidity, and you can start that if you want on the geography on the graph on the left-hand side, you can see the relative humidity going from 20 up to 80. And so we know that between 20 and 60% relative humidity, again between 70 and 82, 83 degrees Fahrenheit at relatively low air speeds, less than 20 feet per minute, that people will be comfortable in this space. So there's 6 reasons why we need to control moisture. We need to control it for preservation of materials. We need to control it for the bugs in the space. We need to control it for respiratory comfort. We need to control it for dimensional stability. We need to control it for thermal comfort. And if we do all of these things, which are far more important things to worry about, then we enable the use of radiant cooling without having to worry about the condensation issue. So my comment to these people that perpetuate the myth that you can't do radiant cooling because it'll condense, they're idiots. They're bad building people, and they shouldn't be allowed to build buildings or do HVAC design. And I know this is recorded that I can't speak. I know this is recorded forever, and it's good. And have those people call me, because perpetuating myths is bad for industry. It's bad for occupants. It's bad for those that do design work. It embarrasses us that have a good understanding of psychometrics and building science. So there you go, gents. 6 very good reasons why you need to control moisture, independent of the type of HVAC systems. And if you do that, then you can do radiant cooling anywhere in the world. I'm done.
As a matter of fact, that you just recently finished up helping the folks over at Uponor develop their radiant cooling design manual. Is that correct?
Yeah, that was actually an interesting project. It was actually Dr. Peter Simmons and I were sort of the outside consultants on that, and that project started a number of years ago and finally got completed here. I think it was this year actually they published it, or last fall. In any event, it's a great resource. They make it available free. I don't know how many pages it is. It's a lot. But would encourage anybody that wants to look at designing radiant cooling systems. That's really one of the places to go. And of course, we have lots of articles that we published recently in HPAC Magazine Canada on designing radiant cooling, and we make all the training programs that we did. Like we did one, I think was it last year, Mark, for Comfort Tech.
Yes.
I think it was a 2-course program that we did on radiant cooling, and that's available online. So there's no shortage of information on how to do radiant cooling. And I know John has done a number of articles, and he's got a book, I think, through the Caleffi series on cooling as well. Is that right, John?
That's right, yes, on chill water cooling systems. I think it's number 13.
Yeah. So there's no excuse for not having that information to do design. So
Robert, Dave Yates sent me a note and said to tell you that the National Home Building Association just called.
Love it.
Boy, if somebody could use some education.
The older I get, the less. Yeah, it's like any other. I mean, I belong to what's called Canadians for Properly Built Homes, as an organization to help consumers that have been stung by the Home Building Association, and certainly, it's like any other industry. There's really good people in the home building industry that are really conscientious. They've got great people on their teams. They build really nice structures, but there's bad apples everywhere, and unfortunately, it's the bad apples, again, those that perpetuate myths or do poor construction, that make it bad for the entire industry. So. I'd be happy to talk to the folks from the Home Building Association.
Yeah, no kidding. I would be glad to arrange that meeting and stand by your side as well. As it pertains to radiant cooling, and I've sat through the course and the presentation that you did in Las Vegas earlier this year, and they had mentioned that the Crystal Mall was a radiantly cooled building. And, this is just the same concept as radiant heating, except that it's on the opposite end of the scale. And it's something that you have to experience before you can really understand the quality of comfort that's associated with it. So I dragged the wife across the street, and we were walking down the strip, and I saw crystals, and I said, I want to go in here. And we walked in, and standing in the middle of this radiantly cooled mall, and I said, what do you think? And she goes, what do I think what? And I said, are you comfortable? And she goes, yeah, it's nice in here. And I said, okay, let's keep moving. And we moved further into the core of the building, where we got out of the radiantly cooled zone and into the primarily convectively cooled zone. And I said, how you feeling now? And she said, I'm cold, I'm uncomfortable, I'm really not comfortable. She said, I like that other area better. And when I explained to her that she'd walk through this radiant zone for radiant cooling exposure, she's like, wow, that's really neat. She goes, that's really graphic. You don't realize until you've experienced it that there really is that big of a difference. And the same thing pertains to radiant comfort as it pertains to the heating side. Most people that have never experienced the comfort associated with radiant heating are basically being left out in the cold, and they just think of heat as being heat. And the general contractor is the worst promulgator of that. When they're building and designing a house, they send bids out for heat, and the guy shows up with a bid that is X amount of dollars per square foot, and it's a fourth as much as the hydronic radiant heating system, and he defaults to that lower value, saying, well, this is what I had, and doesn't give the consumer the opportunity to ask questions. What's the difference between these two? Why is this one so much more expensive? And is this something that's really worthwhile from the standpoint of being able to utilize it? And I know some attorneys that can put a price on discomfort, but when it comes to comfort, they will tell you right up front that it's priceless. You're not thinking about it, you're just simply comfortable. So it absolutely, if you get the opportunity to experience it, do it. We're in the process of trying to put some experiential centers together with some of our wholesalers, and basically set up areas where the contractor can take a homeowner and let them feel the difference between heating and cooling as it pertains to radiant. And one of the questions that always comes up anytime that I'm talking about radiant cooling is, how do you handle the latent loads? And obviously, in some certain situations, if you've got a limited amount of space and surface available, you're also going to have to handle some of the sensible loads with an auxiliary system. And I know that you have addressed it from the standpoint on commercial buildings of using a direct outside air system with the ability to be able to either extract or inject humidity to maintain that 30 to 60% relative humidity range. Is that correct, Robert?
Yes. Yeah,
And,
30 to 60%. And at 60%, yeah, at 60%, you're still well below the dew point. So again, like in terms of condensing, it's a function of moisture and temperature. And on the saturation curve, you can see the wet bulb temperature. So what happens, of course, is that if you're running on floor cooling, for example, say 66 degrees, and where does that number come from? Well, it comes out of the ASHRAE standard that, if you go cooler than 66 degrees, you're going to feel uncomfortable. So if you keep it above 66 degrees, you're fine. So if you just look at the graph and you go up from the bottom at 66 degrees, you can see that, that you're going to end up condensing at 100%. So if you have anything below 60% relative humidity and 66 degrees, you're well within the safety zone of the panel. So you got thermal comfort and you have no condensation issues.
One of the interesting takeaways that I got from that trip to Las Vegas and sitting into the Uponor programs was the fact that the approach water temperature from the chilled water source is typically between 50 and 70 degrees Fahrenheit. And I'm sitting there thinking to myself, it's entirely possible in a properly designed system, in a properly installed system, to do compressorless cooling, especially like in Las Vegas where you don't have a whole lot of latent to deal with. It's all sensible. So if a person's got a ground source heat pump system with either vertical borehole or horizontal field, it's entirely possible that you could circulate water between your radiant panel, be it ceiling, floor, wall, whatever it happens to be, and directly to your loop field, and eliminate the need for any parasitic cost of operation as it pertains to compressors. So compressorless cooling is really not that far into the future. I think it's here today.
No, it's when you look at climates that are relatively dry, and Peter Rumsey, who's just a wonderful engineer out of the U.S., has done a lot of compressorless cooling systems. And one of the ones he did for one of the universities was they used the roof essentially as a cooling surface. So at night they sprayed the water from a cistern, so going back to this gentleman's comment about the cistern in the ground, sprayed water up onto the roof at night, so they had evaporative cooling, plus they had night sky radiation. So between those two functions, they were able to chill the water. That water was collected in the rain gutters off the roof and then collected into a cistern. And then during the day, that chilled water was used to cool the campus, or this particular part of the campus, for the entire day. So there, there's an application where you're doing compressorless cooling on a relatively small building. But on a large scale, the Manitoba Hydro building, which is 23 stories, they're completely connected to a ground system with biases on their heat pumps. And so during the times of the year where they can extract or dump energy, as going back to John's point, where you're actually extracting heat out of the building and dumping it into the ground, they're doing that. And they're bypassing the heat pumps. And the only time they use the heat pumps is when they get into peak loads where they have to kick them in to do the compressor cooling. And they do the same thing with heating. They've actually, their heating pumps are heat pumps in the heating mode, but they have a peak boiler plant for peak loads. So that building, in terms of the concept of exergy, which I don't know if we'll have time in the remaining time here to get into, we should. It should be a topic all on its own. It has a very high exergy efficiency, which means that the fluid temperatures that are required for cooling and heating are very close to the source temperatures. And the ground, of course, is a perfect source for cooling and heating. So very high exergy efficiency.
Is that Alberta Hydro building primarily a radiantly distribution system? Or is it convective? Yeah,
it's actually in Manitoba. It's the Manitoba Hydro one. You can get all the information online, and the whole building is all cooled and heated with radiant. And if you look at high-performance buildings, and this is actually what we're going to be talking about in our heat spring course, if you look at high-performance buildings, they have a number of things in common. One, the buildings are high-performance. The systems are low-temperature heating, high-temperature cooling, so all radiant, dedicated ventilation systems, and all construction of low VOC materials. So tile, slate, terrazzo, exposed concrete, and those materials, of course, not only do they have low VOC content, but they marry beautifully with radiant systems.
Mm-hmm. Yeah, I think that a lot of people are missing that boat, that we are in a position, regardless of whether we're doing heating or cooling, regardless of whether it's residential or commercial, which, by the way, commercially, that airport over in Singapore has been running for better than 20 years on radiant cooling, so it's not a new concept by any means. It's just a matter of us exploiting it as an industry. And I think that slowly but surely people are starting to catch on to what this radiant comfort is all about, and that we are basically in the driver's seat with the ability to be able to make our systems compatible with any energy source, regardless of whether it's Mother Nature, Earth, direct connected, put something in between that, compressor-wise, woody mass, woody biomass, solar thermal, you name it, we're compatible with it, and it all basically comes down to the fact that we're dealing with small bore tubes and the fact that we're controlling and affecting and manipulating the mean radiant temperature that drives the bus of human comfort.
Yeah, I think one of the things I like about what everybody here on the room has been doing, and specifically John Siegenthaler, is really sort of educating industry that radiant and hydronics, but radiant hydronics is an enabler. It enables us to do many things that are good for the indoor environmental quality, which of course by contract is good with the occupants, and it's good for energy conservation and energy preservation. So it's no matter what you want to talk about radiant, it's an enabler, and that's something that you can't debate. It's just science. It's the physics of the whole thing.
It is. We have some questions for you, Robert. Harvey Raymer would like to know, what are some suggested equipment selections for the sole purpose of controlling relative humidity? And my assumption is that it would have to be something that could extract as well as inject. Like here in Colorado, right now we're probably dealing with a 7% background relative humidity, so we need to inject. But later this afternoon, when the monsoons kick in, the relative humidity is going to go up to about 90%, in which case we're going to have to extract. And obviously the direct expansion units are the most prevalent, but are there some other alternatives available on the market that can reduce humidity without having to fire a compressor?
No, it's just all off-the-shelf stuff. It's all off-the-shelf stuff. So you can use refrigerant, you can use chilled water, you can use a combination with desiccant wheels. So that's the nice thing about it, is that when you pull out the sensible load and just assign the latent load to the air handling system, you're just dealing with off-the-shelf equipment. The only thing that you may, like in smaller projects, and again, I'm not sure what his clientele is, whether it's commercial or residential, but if you look at the guys from what Building Science Corporation have been promoting for many, many years, they talk about standalone dehumidifiers. And they have a really neat concept, which I really like, and that is they have a mechanical closet where they're actually drawing return air into the closet, where they have a standalone dehumidifier. And so that air, or that dehumidifier, is dehumidifying the air in the closet, which is then drawn into the return plenum of the air handler and then sent out in the building as conditioned air. So, for small jobs, that's a nice way of doing it.
Did they set that ductwork up?
And as far as controlling,
that's a joke.
I just got it. Yes, a little slow today. All right. Yeah. So that's and as far as so that's in terms of the actual process of removing humidity, and then just standard dew point controls and sort of the brand names and control strategies have that.
Dan Holohan mentioned that when we were talking about the difference between radiant heating and radiant cooling, is don't be left in the cold. That's true. We affect the mean radiant temperature, and this is one of those areas that I'm going to be speaking next week down in a predominantly cooling loaded area of Nashville, Tennessee. And I'm sure that those contractors are going to be looking at me like I'm from another planet when I start talking to them about radiant comfort. But basically they're missing the boat too, because they don't understand it. They're just looking at it as heating and cooling and not necessarily comfort. They all claim comfort, But by golly, bottom line, you walk from a room that's convectively heated or cooled into a room that is radiantly heated and cooled, you can feel the difference, and your body can definitely feel the difference. So it's one of those things that has to be experienced, and we're working on getting some of those centers set up so that they can. Rich McGrath chimed in and said that this is where the thermal battery is really going to kill everything, right down to the first cost. And I'm sure that Colin would probably agree with that. Basically, the ability to be able to use off-peak electricity to generate and store ice for use during peak loading conditions. I mean, these are not any new concepts by any mean, but I think that when they're interfaced with our hydronics, that more of them are going to start making their way to the surface, and people are going to start paying attention to it. Rich has got another comment here that says, no other segment can deliver comfort as well as us, and that's true. And I see Colin's chiming in. Colin says, we are on the cusp of hydronics and radiant revolution, and get ready all, for when the general public finally grasps what it is that we're ready to do, we're ready. We're all standing here going, yeah, we've known this for over 100 years, and we've been beating the band, and part of my job as the executive director of the RPA is to move the needle. We've been doing the same thing that we've been doing for the last 20 years in promoting warm floors, and I blame Richard Chathui for that. He showed up on this old house with a 1,000-foot roll of PEX on his shoulder and said, we're going to do radiant floors today. And that, in my opinion, was the kickoff of the radiant floor revolution. But we need to take the focus off of warm floors and put it onto radiant comfort, regardless of what the emitting surface is. And in doing that, we're going to find that we can do the installation cost for less than what it would typically be if we were doing 1 linear foot of pipe per square foot of floor, and still deliver good comfort. I know that we have one member in California who is doing nothing but radiant ceilings, and he's actually gotten the cost down to the equivalent of a gas forced air distribution system. So you got to think outside the box. It's not just the contractors that are looking at me from like I'm from another planet when I tell them that warm floors are great, but they're not the end all. And we as an industry need to start putting more attention to the focus of radiant comfort, regardless of the emitting surface. If the person wants warm floors, absolutely, sell it to them. They better be able to afford it. But as it pertains to radiant comfort, we can do it without having to do 1 foot of pipe per square foot of floor space, and move the needle so that we can start proving to not just the consumers, but the government and industry that we are, without a doubt, the best. They've proven it. I know, Robert, you've taken the tour of the NREF facilities up here in Colorado with the radiant ceiling heating and cooling system in it.
No, I haven't taken the tour. They wouldn't allow me there because I didn't have my my passport clearance. So when we went down to Asheray, you had to go through a security clearance, like a pre-screening.
Yeah.
And because I didn't get my passport into them in time, I didn't get a chance to actually tour the facility. But I'm very familiar with the project, and because I work hand in hand with Uponor, and they of course supplied the pipe on that, and I know a number of the guys from the actual campus itself there, and I've talked to them at length on their building. So
yeah, John and I actually took a back.
A couple of questions that you. Oh, did you? Well, you're American citizens, and So, a couple of comments. One of the other myths, because since we're talking about myths, has to do with, and you brought it up, is cost. And we know on the commercial side for sure that the hybrid systems, where you're doing dedicated outdoor air systems with the radiant, that these systems are actually coming in less money than the traditional VAV system. And a good example of that large-scale building was the one in India, again, another Peter Rumsey project. And they right now it's the world's largest side-by-side comparison. I can't remember the name of the client, major computer company, IT company in the world. And half the building was done with VAV, half of it was done with radiant and dedicated outdoor air systems. And the hybrid system came in less money than the VAV system. It operates at less cost, and the people are much more comfortable. So there you have a really large-scale structure, side-by-side comparison that's demonstrating that you can do these systems for less money than a traditional air system. And the other comment I want to make, and John probably has some good words of wisdom on this as well, and that has to do with, and we talked about it, the trend in high-performance buildings. When we talk about radiant, we want to be careful that we don't start to argue with the science behind mean radiant temperature. In other words, the mean radiant has a big role to play in thermal comfort. In fact, I've said numerous times that if building codes changed the requirement from air temperature to mean radiant temperature, buildings automatically overnight would have to improve, because in order to control MRT, you have to control the building. In order to control air, you can have a crappy building, right? So MRT is really important. But as we see buildings improve, the building actually solves a lot of the radiant discomfort. And so we can go into the future, certainly, espousing the comfort, the thermal comfort part of it, but at some point we're going to reach a place where buildings, mainstream buildings, are high performance, and the argument for MRT is solved in those structures. And so the radiant or the hydronics, that argument, of course, becomes diluted. That doesn't mean that we should ignore other benefits, and that again is enabling the use of low temperature energy sources for heating and high temperatures for cooling. And at the end of the day, like 100 years from now, when we look at buildings, that will be the big story for radiant, in my opinion, is the fact that we can heat and cool without combustion and without compression.
Understood.
John, I don't know if you have any comments on that.
Yeah, absolutely. Your interior surface temperatures are going up as you add R value to the thermal envelope, so your MRTs are coming up. And agree. We talk sometimes about radiant panels or hydronic distribution systems that use low water temperatures as future-proofing the distribution system, with the idea that initial heat source might only last 20 years, and a well-designed radiant panel could last decades longer than that initial heat source. So in a sense, you're bargaining on the fact that the future heat source, if you design a high-temperature system, you're kind of gambling that the future heat source will be compatible with that, and I don't think that's going to be the case.
Rich McGrath put in a note that will answer your question, Robert. He said that everyone should check out the Infosys report from the building in Hyderabad, India, and that was the one that has just recently come out that had the forced air system on one side and the hydronic radiant on the other side, that was seeing such a significant reduction in cost of operation and increase in comfort and everything else. So yeah, if you get an opportunity, right, I would Google Infosys building in Hyderabad, India, and get that report. I've seen it. We actually ended up distributing it. In fact, I think it may be available from the Hydronics Industry Alliance commercial website, which is hydronicindustryalliance.org, which for those that are a commercial hydronic manufacturer, you should be a member of that group. They're making some substantial inroads into making sure that hydronics stays where it is and increases its market share. But we shared that report with them, and going back to what you said about the mean radiant temperature, you're absolutely right. These super insulated buildings, the MRT is coming up. But if we want to keep our cost of operation as low as possible, we still hold an edge. And moving air is not an inexpensive proposition. There's just some parasitic cost of operation which are impossible to avoid. Do we have any other questions for either Robert or John? 2, 3, 4, 5. I don't see anything, so I think that it is time to go ahead and move on. And our moving on basically means thank you very much, Robert and John, for your explanations, and I'm sure you're going to stick around here for a little bit to answer any questions that hopefully will pop up in the next few minutes as it pertains to systems in general, which now we begin our open Q&A session. So if you've got a question about a problem that you're having with a hydronic heating system, by all means type it into the chat box, send it to me. I will present it to our group of panelists, and we will all chime in and see if we can find a solution to your problem. And I don't want to say I'm the best troubleshooter in the world, but there have been very few systems that have ever stumped me. And the one that really had me going for a long time was a system that I ended up getting dropped into the middle of in Cincinnati. And this is clear back in like I think it was 88, something like that. And the Democratic National Convention was going to be staying in this hotel. And I get a call, and they said, we need you out here. We just lost our cooling system, and we've got a full hotel. And I went out there, and it was one of the scariest systems I've ever seen. It was a high temperature, high pressure hot water heating system. It was running at 250 degree Fahrenheit water temperatures and using very small heat exchangers to transfer that energy into the actual distribution system for the building. And actually used a nitrogen charged expansion tank to maintain high pressure on that 250 degree Fahrenheit fluid so that it would not flash to steam. And talk about your sphincter doing the mamba. As I'm walking around in this mechanical room looking at all this equipment and this boiler that's as big as my house, it blew me away. But I spent 16 straight hours in there making drawings of everything that was there. I saw one electric motor that was running that had nothing connected to it, and when I pointed it out to the chief engineer, I said, "What's this?" And he said, "Well," he goes, "I don't know," but he said, "If you shut it off, it shuts off 2 other pumps, and then we have nothing." Like, okay, you've got issues here. Let's just keep moving. So does anybody have any other questions that they would like to ask of our guest panels as it pertains to the open Q&A session? I'm not seeing any. Well, gee, guys.
We could throw out some other myths.
Yeah,
people are.
Yeah, like that myth that we started to touch on, that hydronic radiant heating and cooling systems are not applicable in high efficiency houses, passive houses, etc. And I just finished an article, Killing Myths, doing basically the same thing for our industry. And I'm talking to contractors that are building these super insulated houses, and I said, "What are you doing for domestic hot water?" "Well, I got a 120-gallon storage tank down here in the basement with 199,000 BTUs per hour because the lady's got a big soaking tub that she doesn't want to run out of hot water with." "Great. And what are you doing for heating here?" "Well, I can't find anything small enough to handle it, so we're going to have a little bit of short cycling issues." Well, geez, guys, you got a huge buffer tank with all the energy you need sitting right here that's used for maybe 2 hours a day, that we could very easily latch onto that and use that for doing radiant comfort heating through panel radiators in the ceiling and reduce your installed cost, increase the human comfort factor, and reduce the operating cost of the system. So, these guys that are saying that we don't have equipment small enough are sitting there looking at another piece of equipment that has to be much bigger, that we can utilize for the 22 hours a day that it's not being used for domestic hot water production. We just have to think outside of the box. Don't let them put you into that box and say, "No, you can't do it because you don't have any equipment that's small enough." It's all a matter of understanding what you've got to deal with and how to work with it and how to make it work. What other myth would you like to kill today, Robert?
Well, one of my favorite ones is that you can't do radiant heating in passive heated homes. And the argument that always comes up is that, well, if you have all that solar gain in the building, it's going to overheat the space because the floor is already warm. And people tend to forget that in a high performance building particularly, even during the evening on a really cold night, you may only be running 85 or 90 degree water temperature through the floor. And to put that in perspective, that's cooler than body temperature. So as the sun starts to shine on that building, and if it comes through the glass, and I don't know how many of you have done this, but if you take just a regular thermometer and put it on your floor without floor heating, that floor gets to 85, 90 degrees Fahrenheit without any extra heat. So if the water temperature in the system is 85 degrees and the sun is heating the floor to 90 degrees or 95 degrees, the floor is cooling. It's not heating. So how can it be contributing to overheating in the space? So that's one of the myths that drives me crazy. Again, people not understanding the physics of buildings and systems. So anytime the space is warmer than the floor is cooling, not heating.
Mm-hmm. Dave Yates sent in one. He says that you can't use a mod-con boiler with hot water baseboard.
Well, I'll jump in on that one.
Go for it.
Yeah, there's a number of products out there now that are actually designed around water temperatures more, designed low conditions, 120, 130 degrees. So there are baseboards specifically designed for these low temperature systems. And I think what Dave's probably talking about is standard baseboard. And if I'm guessing what his thoughts are on this, is that with outdoor reset control, there's a lot of operating hours at partial load conditions where the water temperatures, even in standard baseboard, could be in that 120, 130, 140 degree, perhaps even lower, so that the boiler actually will operate to a degree in a condensing mode during those part load conditions. And I think Brookhaven Labs actually did some analysis of that based on bin temperature data and found that it was justified to go to a ModCon boiler with even standard baseboard.
Sure. I think another factor that a lot of people are missing is the fact that that whole hot water heating system was designed for design condition, which occurs for less than 2% of the time.
Right.
And for a lot more of the time, you can operate at supply water temperatures significantly below design condition and still make it work. Plus, there's the opportunity of conservation efforts that have been done, extra insulation, storm window changes, etc., that makes the baseboard oversized, which means that you can do it and it'll work great. But a part of it has to do with consumer education. You have to explain to them that when you turn the thermostat up, that baseboard's not going to vomit heat on your body like it used to. Just set it and forget it. Don't turn it up and don't turn it down. Set it in one position and leave it alone. Don't worry about using nighttime setback thermostats because the conservation effort is now being done at the source of supply. And they work great. I mean, I've had apartment complexes where we've gone into and the only thing we did was changed out the heat source from a conventional atmospheric at 80% to a 95% ModCon boiler and reduced the fuel consumption of the building by 50%. Now, 50% is not something that you can sneeze at. That's a pretty significant number. The minimum I saw was 30% reductions in consumption, and the boiler didn't care. It worked just fine as long as they're maintained. And that is a big downfall in our industry, as there's a lot of boilers that have been installed that are not being properly maintained. And I unfortunately have had the opportunity to see what happens there after the fact, and it's not pretty. So if you've got them out there, maintain them. If you're not going to maintain them, find somebody that will, and make sure they're taken care of. Otherwise, our industry is going to get a black eye from something that we thought was the right thing to do. I have a myth. You can't use radiant floors with hardwood flooring because the floor surface temperature is not allowed to be greater than 85 degrees Fahrenheit. And I actually have pictures of my own house in my front living room area. I don't have radiant floor, I've got panel radiators. And I took a picture with my infrared camera with the sunshine coming through the west facing window and landing on the floor. And the floor is at 120 degrees. So I took that picture and sent it to the National Hardwood Flooring Association and said, am I going to have issues? And they said, oh, you must have radiant floors underneath. And I said, no, I don't. I said, that's just sunshine falling on the floor.
Yeah.
Is my floor going to suffer any kind of substantial consequence because of that? And we're actually working with them now and redeveloping what they had originally put together in a way of guidelines. And this is done back under the old Radiant Panel Association with Larry Drake. And Larry Drake had told them that you have to limit the surface temperature of the floor that you're in contact with to 85 degrees Fahrenheit. Well, they somehow took that information, and I've had flooring contractors coming back to me saying, well, I heard that we can't have supply water temperatures from the boiler of greater than 85 degrees Fahrenheit where hardwood flooring is in the configuration. And it's like, I don't think so. And it's going to take more temperature than that. And, you just need to do the science, run the numbers on it, and figure out what you need in the way of a surface temperature, and then work backwards from there till you get to the heat source and say, okay, at design condition, this zone needs water supply temperatures at X degrees Fahrenheit. But I said, don't limit it to 85 degrees Fahrenheit, or we're both going to have dissatisfied customers. And such was the case. So radiant floor heating done properly, and again, to Robert's point, humidity control is critical with these hardwood floors. And that's an area that is so often overlooked by our industry that it just makes me want to pull my hair out. They all go, yeah, I'm just here for the heating. Well, you're an environmental contractor. You're supposed to be providing comfort. You should be doing humidity. You should be doing filtration. You should be doing the outside air introduction. You should be doing the heating and the cooling. But, the different divisions are so segmented and so broken up that it always ends up a big circle jerk of people pointing fingers of blame. It's your fault. It's your fault. It's your fault. And nobody wants to assume responsibility. Well, as a comfort contractor, if you assume all environmental considerations, you're point responsible for everything. And if you're doing it right, you will have no complaints. Zero complaints coming back to you at all. Here's one from John. It doesn't matter if the tubing is left at the bottom of the slab.
Yeah, we've had that debate a number of times where tubing is typically tied down to welded wire reinforcing mesh, and it sits there on top of the insulation. And some contractors just dump the concrete on top there with no attempt to lift either the mesh or the tubing, and off the top of their head say, well, it doesn't matter whether the tubing's up in the slab or laying at the bottom of the slab. And we have looked at that again with finite elements, and we do see a pretty significant difference in temperature. One of the things that is a point to be made in a discussion like that too, if you look up the guideline specification for welded wire fabric reinforcing, this is the light gauge sheet or roll good steel wire reinforcing. The specifications call for that to be between 1/3 and 1/2 of the depth of the slab down from the top, not laying at the bottom of the slab. So even if you took the tubing out of the picture, the structural performance of that wire at the bottom of the slab it's not there to the extent that it would be if it was installed properly. But on the thermal side of it, we looked at a 4-inch slab with the tubing at the middle. We actually modeled the tubing at different heights in the slab, but I'll just reference the tubing approximately in the mid-height of the slab versus at the bottom of the slab, and with an output heat flux at about 15 BTUs per hour per square foot, it was about a 7-degree increase in water temperature with the tubes at the bottom of the 4-inch slab versus approximately at the midpoint. And then if you double that output, if it's a building that requires 30 BTUs per hour per square foot, it pretty much doubles the delta T. Actually, it was up around 15 degrees higher water temperature. And also, the downward heat loss through the insulation increases as the tubing gets closer to the bottom of the slab. So again, based on some modeling, it does make a difference. So I just want to throw that out as a point. I suggest to people that their drawings and their specifications are very clear on where that tubing should be in the slab, and also that there's good communication with the contractor that's going to be placing that concrete, so they understand that it does make a difference where that tubing goes, and the specs and the drawings call for it to be approximately in the midpoint of the slab. Now, if you're lifting the mesh and the tubing during the pour, it's not going to be perfect, but it's definitely going to be an improvement over the tubing and the mesh just lying there on top of the insulation. We did see a project. We did have a project once, Mark, with a 6-inch thick concrete slab, and the tubing and the mesh were left at the bottom. And I can tell you that the lag of that system was very noticeable compared to other slab-type projects where the tubing was lifted.
I just went through this very same process in my daughter's house. She's building a house here in Denver, and I'm her consultant, of course. I'm not doing the contracting, but it's a 6-inch thick structural slab. And I said, we got to lift the tubing at least 4 inches to get it up to the height where, it'll be within a couple of inches of the surface. And the GC was willing to acquiesce and went with Adobe bricks to hold the tubing up to that point. And he looked at me and he says, do you got any ideas about how we can keep these 200-pound concrete guys from stepping on this stuff and pushing it down to the bottom of the slab? And I said, yeah. I said, just have them to flap their arms really hard, and they'll elevate, and then they can get their job done without having to worry about it. He thought it was serious.
Well, yeah, that's the problem with putting light gauge wire up on supports. It's very, very difficult to walk on it without bending it all up. It's impossible. So we advocate rather lifting the mesh and the tubing as the concrete's being placed. And from what I've seen, it works reasonably good, provided the person that's doing the lifting stays with that lift hook, and just that's their function during the pour, is to make sure that material comes up, it's not to go grab a rake or go get the donuts or whatever. It's to make sure that they're getting that tubing and that mesh approximately in the middle of the slab.
You know, it's one of those things that you don't realize its negative impacts until it's too late, and then there's nothing you can do about it.
That's right.
You know, it's a shame, and I guess we as an industry need to start pushing this point more to our members so that they can push the point more to the general contractor so that we can avoid these issues. But good point. Rich McGrath had a question for you real quick before we get to the end of our session here. It says, question for John S. With low temp systems in buildings with a lot of thermal bridging, why do some ignore this area for tubing? Mean radiant temperature can be hurt. The area below cabinets.
I'm not sure I'm following the thermal bridging part of that.
He's talking about the area below cabinets, for instance.
Okay, we've got area below cabinets. Is he talking about not putting tubing in there?
I think he's wanting to put it in there to be able to counter the negative effects of thermal bridging within a wall.
Well, I would go with a good edge insulation as opposed to putting the tubing under the cabinets. The problem with tubing under a cabinet like that is if you store food in the cabinet, that the cabinets will get noticeably warmer, and that's going to affect the storage life of the food.
It's great for growing potatoes and onions.
Well, yeah, and I mean we've seen this not only with that, but just food in general. You know, and we've also seen situations where without a tubing plan, contractors will install tubing under areas where a refrigerator or a freezer is going to be placed. Which, you know, you think about that, it doesn't make a whole lot of sense to put a heated floor under a refrigerator.
No, it really doesn't. Anybody else care to bust some more myths? By the way, Rich McGrath is familiar with Martin Holliday.
One.
The Tres Amigos.
Yeah, our buddy Martin. No, Martin's a good guy. He's not an idiot. He knows his stuff, but he has some biases towards things that would probably change. You know, if he maybe had some experience with the systems that we're talking about. But I'll keep also in mind he's very much a minimalist, and so you know you have to sort of take him with a grain of salt, and same thing with you know sort of the other colleagues that he hangs around with. You know, one of the interesting things is Martin's a big fan of Dr. Seabrook from Building Science Corporation, and if you talk to Joe, Dr. Joe, you know, he's a big fan of radiant heating. So there's a conflict right there between those two individuals. Same thing with mini splits. I know Dave line, but you know, Joe hates mini splits for the same reasons that I hate mini splits, and you know they're I think they're ugly, but some people like them. Yeah. Hey, listen, I got one of the ones that we always come across, and which is a silly argument. That is, that people talk about, you know, you need a separate air system with radiant systems, and there's two responses to that. And the comment you typically comes across like, well, you need to move air in a space to be comfortable, and so you're going to have a separate air system. Well, in fact, moving air is not necessarily a comfortable thing, particularly if you're cold. If you're hot, it's a great thing, but if you're cold, it's not. And if you go back to the fundamentals of design of radiant systems, 50% or roughly 50% of the heat transfer coefficient in a radiant system on a floor is convection. It's air-based. So you have actual natural air convection in a space with radiant. And then the third thing has to do with air quality. And oftentimes you hear people say, well, you know, with radiant or hydronic systems, you have to put in an air system anyway because you're going to need to be moving air. So why would you have two different systems? And in fact, when you look at people that are very respected in the industry when it comes to indoor air quality, all of them, there's no exception to the rule, all of them will say that for really good indoor air quality efficacy, you should have an independent ventilation system. So again, going back to those that have knowledge of these requirements for indoor air quality, and those that don't, those that have the knowledge will say have an independent system. Those that don't have the knowledge will say, why would you have separate systems? So if you ever hear that argument, again, people say, well, you need to have a separate system, just point out to them that the experts all agree that you should have a separate system. It's the best. It's the way to do it.
I agree. No argument from this end. Anybody else got any myths that they'd like to quash at this point in time?
Well, there was a good comment by Harvey with regards to slabs and no insulation. And I don't know, John, if you can see the question there. I'll let you take it. I can answer, but I'm gonna just shut up for a little bit.
I'm not seeing his question here.
Okay, well, I'll read it. I'll read because it's a great question. It's something we've addressed a lot, but I'll read it and you can answer it. He's saying in a building that has that slab on grade, I've noticed that with uninsulated slab, the building reaps a lot of cooling benefit and a low temp heating benefit directly from the earth. An insulated slab doesn't have these benefits, but is required to achieve normal levels of heating. Is there any possible way to integrate radiant heating that would take advantage of the uninsulated slab?
Well, I wouldn't want to go there. I'm trying to think that one of the points, if I'm understanding it, is he's looking at maybe this time of year, or September, October, where the Earth is relatively warm based on its annual cycle. Is he looking to actually transfer heat from the soil under the uninsulated slab and maintain comfort in the building under those conditions? Yeah, I could see where an uninsulated slab may do a little bit at the beginning of the summer as far as absorbing some heat, but you have to be careful with that. I mean, mildew problems, moisture problems, something along those lines. I'm a big advocate of under slab insulation, and Robert, you and I you've done an excellent job with the documentation of some forms of under slab insulation as being not really adequate. And one of the points that we both made, it's very difficult to retrofit under slab insulation. In fact, I think Mark Rosenbaum actually used something like that the other day in one of his webinars, and I totally agree with him.
He did.
You got one shot in the life of the building to do that under slab insulation right. So, a good proven material, a polystyrene material, and don't scrimp on it. For me, I would look at an absolute minimum criteria as the under slab R value being at least 10 times the floor covering R value as a minimum. And I think that goes way back into some European recommendations. I remember seeing, gosh, probably 15 or 20 years ago. So if you're going to put hardwood over a slab, or if you're going to put a carpet, a pad, something like that over it, even an R1 floor covering, you should be looking at least an R10 proven material under that slab for insulation. So I guess I would not be in the camp of going for any kind of uninsulated slabs with radiant heating.
So, like, just roll out one little piece of bubble foil bubble, and that'll give me an R10, right?
Yeah, I thought about talking about bubble foil, but I'm not sure we want to go down that road. But again, I'd recommend what Robert's done with healthyheating.com. He's got very extensive references on some work that have been done that really shows the inadequacy of some of those products under a slab like that.
Yeah,
I've actually done some research with snowmelt systems. I did a study for an article that I wrote a long time ago that is out there somewhere. And one of the interesting things that I noted was that when I showed up on a Saturday to pull the sensors and the data loggers and stuff, I had my infrared contact thermometer with me, non-contact thermometer, and I shot the slab, and it had been a clear night the night before, and the slab was about 15 degrees cooler than the surrounding ground. And the system had actually had to fire that night before because it had a moisture occurrence. And I got to think about that. It's like, if I didn't have the insulation underneath that slab, I wouldn't have had to have fired the system because the ground was actually at 40 degrees. And my minimum set point on the controller was 40 degrees. So even though it sensed moisture, it would not have fired the boilers. But due to the fact that the slab was isolated with insulation and night sky radiation had cooled it down, then it went ahead and fired. But I agree with you, John, and I agree with you, Robert. You have to have total control over the flow of energy into or out of any scenario. And if you don't put insulation in there, you have no control. And when you do need that snowmelt system, you're going to pump a whole lot more energy in there, not just into the slab, but also into the ground to bring it up to equilibrium before the heat starts coming up to the surface to melt the snow. So, Harvey, I hate to tell you this, but they don't make a portable insulation yet. Maybe one of these days they will, something you can flip a switch and make the insulation disappear. or flip it again and have it come back on. But for the time being, I think the consensus is insulate. Robert?
I think one of the challenges with any discussion on ground coupling, it has a lot to do with the characteristics of the soil. It's as much as we like sometimes to treat these discussions as sort of ones and zeros and black and white, they're in fact very gray and fuzzy. And downward loss is one of those things, because you can change the soil types, the moisture content, the aspect ratio of the building, the geology below the building, the activity or the transient characteristics of the water table. All of these things have an impact on the heat flow to and from the slab. And if it was the same everywhere and the conditions were predictable, then it simplifies the problem. But often it's not the case.
And Harvey actually sent in a follow-up. He said this would not be with tubing and floor. So he's evidently speaking about a slab-on-grade application or a situation like I have here in Denver. This house was built in 1955, and they didn't insulate anything. And I have good earth-ground contact, and my mean radiant temperature down here is always cooler. Even though the air temperature is showing 76 degrees, environmentally it feels cooler. But I still, even if it's an unheated space, I think that having insulation in there is going to reduce your dependence on foreign oil or carbon-based energy at all. Dave Yates sent in a note, and it fell off my screen. Go ahead, Robert. I'll find the note.
Yeah, I was going to say, like even without radiant systems, you still have to concern yourself with moisture. So set aside the discussion on temperature for a second, and with not talking about embedded pipes in slabs, but if you've got a slab sitting on cool soil and you have an increase in the humidity, then now you have a potential for condensation on the concrete, which oftentimes is going to be covered up with a floor covering of some type. So independent of the discussion of radiant, by having coupled slabs to ground temperatures, you're going to be the victim, or you're going to be susceptible to any other conditions in that space, which could lead to condensation on the floor with or without pipes in it. So decoupling the slab from the earth does prevent that slab from cooling down to earth temperatures and mitigates to some degree the condensation problems that can occur.
Yeah, we saw a project, this going back again 25 years ago. It was an unheated basement slab in a condominium in upstate New York, and it was May, and got a call to go down and take a look at this, and actually if you took your shoes off and just walked in your socks across this floor, it had carpet on it. So an uninsulated slab, probably 7 feet below grade, with carpet on top of it, and it literally was a sponge. I mean, you could literally, your socks would be saturated the minute you put your foot on it. And not only the moisture, but think about what's going to follow with the mildew and mold problems. A very, very serious situation. So, uncouple that slab.
I agree. Yeah. I found Yates' comment. He said flywheel effect too, and I know Robert has produced a number of articles. I think there was one recently that you had provided information on a house down in Texas that was built to commercial construction standards that was obviously quite mass intensive and had one of the lowest energy consumptions per square foot of any comparable buildings in that area. And I agree with that premises if it's controlled, and that's the key, is controlling it. I mean, it reminds me of a conversation I had with Larry Drake one time about whether you could use a unheated radiant floor to do bidirectional heating. And they said, yeah, you can if both loads are identical at all times. And I said, when you find that building, let me know, because it's going to vary. People doing, body heat in one space that's not in another heat, or in another space, that space is either going to overheat or underheat. So in order to control it, you've got to have control of the surface, and you have to have control of the direction of the flow of energy, and that requires the placement of insulation. Speaking of mass, we have a webinar that's going to be coming up on our Lunch and Learn from a very interesting company that has a phase change material that is not salt based. and this stuff comes in sheets, and they're actually incorporating it into radiant walls, floors, and ceilings, and it basically gives you the ability to be able to store energy, and they can adjust the actual temperature of phase change for these materials. So keep an eye out for that coming out in the newsletter from the RPA about potential applications that are way outside of the box that have huge potential as it pertains to impacting energy consumption. I mean, he's talking reductions of 15% just by employing these phase change materials as a part of the structure. Any other comments? Mr. Miller said, "Sorry, gents, I have to run. This is really awesome. You guys keep up the great work," and he hopes to be allowed to come back soon. Well, in 2 weeks from now, Mike, you'll be allowed to come back in again. We'll definitely be sure to send an invitation up to Canada, seeing as how he works for TACO, and TACO's a part of the RPA family. I see no problem why we can't let him back in. Well, I think that we have basically reached the end of our show. I would like to thank my co-host, Dave, who has been muted, and hopefully we'll have these technical issues worked out before the next show so that I don't have to keep him muted, because he's a lot of fun to talk to and listen to. And our guests, John Siegenthaler, Siggy, and the Bean. And, of course, all of our attendees for taking the time out of their busy Saturdays to come in and educate and learn. And hopefully we kept you somewhat motivated to come back in 2 weeks. So with that, I would like to thank everybody very much for their attendance, and tell you to come back again in 2 weeks when we will be featuring Mr. John Barba, who is another Chowie Award recipient, and some other TACO Comfort team members. And that will occur on September 20th at 12 noon Eastern. I will be transmitting from 8,000 foot in elevation. If you thought I was high now, you should see me when I'm up there. And again, if you have someone that you would like to have get admission to this, have them send me an email. And if you have suggestions that you would like to see for people to come in and be our guest speakers, again, send that information to me. And with that, I will bid you all adieu, and thank you very much, and have yourself a wonderful weekend. I'm headed for Nashville with Dave Yates, and we'll talk to you all in 2 weeks. Thank you.
Thanks, everybody.
Much.
Bye now.
Have a good day.
Take care.